Okay, so we just wrapped up launching one of my local favorite chemicals. Man, I don't know if it's the camera, but I think I need to sleep a little more. Looked at that. I told you a little bit about my adventures in Japan and some of their energy issues. We're also looking at these bizarre commodity spot prices for coal, which I'm still having trouble wrapping my head around. I hope somebody can explain that to me, because I just discovered that going through 214 the other day. Okay, so let's get back into 244. Oops. 244, bioenergy. We're in week 7. This is pretty much hump week. We're next week is all downhill, and I don't see any other. Well, let me take a look at this. 2 paths. I just want to catch up on some. I like your view there on GMOs, yeah. Yeah, I don't think there's really any turning back. Nah. Jason, naughty list, people. This is true, and that's true in just about any market. I don't know if you guys had a chance to read that book that came out, Boys in the Boat, but it talked about how, back in the previous turn of the century, there were a lot of tinkerers trying to build their own cars, but once Henry Ford can make his car cheaper with fewer parts, fewer time, fewer people, they're going to win. And I think that's what Monsanto does. And it could be that, well, I don't think it could be. I think they actually are engineering organisms that have to be engineered. That's a problem I see. And I guess the point, though, as long as everybody else doesn't just give up and continue to keep their heirloom seeds, all is not lost. And I think diversity is the key. And well,
yeah, that's a good point.
Yeah,
diversity is a requirement for success for that.
The last I read, Costco is refusing to sell GMO salmon.
Oh, really? Costco is, huh?
It was the same with Walmart stopped buying milk with bovine growth hormones because customers said
they don't want it. Well, yeah.
And they actually, Walmart's kind of credited for single-handedly changing the bovine growth hormone issue in our dairy supply now.
I'm not really a Walmart fan, but I guess they're really doing a lot for sustainable seafood.
Yeah.
Corporate dollars make the world go.
Yeah.
And if they say we're not going to buy it if you produce it like that, then the producers stop making it.
Well, and I guess and Joe's making an interesting point here. If and when the climate takes on a big change for the worse, we may sort of be stuck with GMOs that can survive those conditions. In fact, I've got a paper that came out just last year looking at the survivability of Arabidopsis in the face of drought, and kind of just figuring out what nature does on its own to be able to do that. Yeah, so I think it's pick your poison. Good discussion though, guys. Wow, that's really good. Thank you for that. That's fantastic. Fantastic. And I think I might have had, I maybe should look at the week 5 discussions too, just a little bit. Don't get me started. Your easy cardboard. Yeah. I've just been taking any cat litter I find and putting it down the sewer lid in my backyard. You know, I don't have a garbage to the landfill, so I just kind of trickle it down. It's poop. Yeah.
I've been actually separating, taking the feces out because you got parasite issues with cat feces.
Yeah.
I've just been flushing that.
Yeah.
City sewer deal with that.
Sure.
And then the
Leftover litter.
stuff, I've been trying to compost.
Yeah, how's it working? The composted
Right now,
cat
I
litter
have
gets a little
water
mushy.
Issue. Well, right now, the stuff I'm using is clay based, so with the extra water, it's
Oh.
kind of nice because it kind of soaks up that water, but then it turns into like, well, you know, when clay and water are really weird, you need drainage, mushy.
Yeah, I noticed that too. I want to, what chemical composition?
But like I was reading about, you know, urea, when we were doing the compounds, you know, it's actually nitrogen mainly.
It's beneficial.
actually really good for composting, so that's why I'm like, well, I'll put the clump of pea balls in compost.
Yeah, totally.
I don't compost for, that compost I don't do for my vegetable garden.
Right, yeah.
If I can put it in, you know, like the shrubbery or something, maybe around the apartment. But it's, right now, I'm waiting for some more heat.
Dried ground clay.
Yeah, totally.
At least they're not frozen solid anymore.
Trying to chip to the middle.
Compost ice age is empty. But it's been interesting, so I've been throwing just a smidgen of plastic in there, just to kind of clear out a lot of paper, sawdust. So I've been trying to compost more of my rabbit litter and whatnot.
Mm-hmm.
And well, so much of that is kind of about the size of the size of your range, you know, like how much space do you have?
Yeah, unfortunately, I live in apartments, I don't have a lot of space.
So that's kind of good news on the cat litter. I hadn't seen this before. I mean, it looks like it's just dirt.
I mean, most, they're clay-based, there's a lot that are like walnut shell-based.
Yeah.
And stuff like that.
So I don't feel bad at all now about chucking that in my compost. I mean, I don't put it in my garden compost. I put it in my just topsoil compost.
Sure.
Wow. Sweet. There's also a brand called Sweet Scoop that's made with,
Oh, it's made with some kind of wood pellets or something.
yeah, it's just agricultural
Like
waste.
some wheat shaft.
Yeah, exactly, wheat shaft, yep.
You know, if you compost it in clay, you just hit a sand, you know, just kind of offset something like that.
Guys, just since you mentioned it, this summer, I'm gonna build a water catchment device out of glass wine bottles.
Nice.
I don't know if I'm gonna try to patent the thing or not, but I've got a student over here next door at Sentinel by the name of Jesse Zhang. He took the practicum last summer. His mom wants him to take it again, so he's gonna take it as $295, and I'm gonna have him 3D print. I'm gonna have him 3D print a sort of a valve that a wine bottle sticks into. And then what we're going to do is have water come up and just sort of sit at the bottom of the upside down wine bottle. And then we'll have another air tube that comes to the top. So as water flows in, air flows out. And we're just going to put those in an array, and it'll be the perfect Missoula Valley hippie wine bottle water catchment thing. So
And then you said that to do like a slow drip feed to.
yeah.
water.
So the idea is to have like just an array, you know, as many bottles as you like with the tubes set up, and then near the gutter will be sort of a water capacitor, if you will. So the water comes in and then like slowly drips up into the bottle because the tubing's small, so you know, big down, so that you've got a water capacitor. Then the water barrel and the wine levels are at the same hydrostatic level, and then from there, yeah, you could put it on a drip or whatever. I also would love to see that as a solar thermal too. So you let that get hot during the day and pull it in at night, and just let that heat content move back and forth. So I'm glad you mentioned glass bottles, because there's so many things we could be doing with that. Okay. Plastic bottle. Burnable pellets. There we go. Doty. Seattle. I just learned yesterday that some of St. Patrick's hospital waste goes to Texas.
Yeah, there's a lot of toxins in Texas.
That's the place for it.
The whole refining industry is in Texas.
It just blows me away. You're trucking that stuff so far.
Yeah.
It's a long one.
I gotta remember who, I think it was Sean was talking to me about Seattle trucking like 40 miles down the road. Just, I don't know. Kind of like not like dealing with the issues. We'll just send it to those guys and let them deal with it. Pretty much.
Yeah, I was just out at Republic the other day. I just happened to be pedaling by, and I'm like, it seems like they're doing a pretty good job at the recycling station. They're sorting through it. And I asked, I think I have his business card here in my pocket. It was a really positive interaction, super positive. Dave Seaberger sat down. I said, hey, what if I had a styrofoam bin sitting here? Would you? And he goes, well, very responsible answer. He said, I'd be willing to give it a shot. The problem we have in Missoula is like once you open that tap, it's kind of hard to shut it off, right? Because everyone's looking for an outlet for their stuff. So another project that I would love to do, also through the practicum, I'm not sure what student I'm going to set this task to, but just take that styrofoam, because what he says, when they squish it, it just kind of disintegrates and turns into a little powdery mess that goes everywhere. So what I would like to do is re-extrude it. So just heat it enough, some kind of solar thermal, solar forge, water bath, whatever, and just re-extrude it into building material. There's all kinds of styrofoam being used in buildings these days. So yeah, that's your number 7. Or no, it's number 6. 7 is other.
I helped build a foundation for a house with my dad this year using the styrofoam blocks.
You did?
Yeah. Concrete fill, styrofoam blocks.
Yeah.
They're awesome.
It worked out great, didn't it?
They're like Legos.
Yeah.
You put them together and you get in there with some little wire framing on the inside of the blocks. And you put the wire framing in, put some rebar down, and then you just pump those suckers full. And it's an amazing foundation.
Yeah. Was there a brand name for it?
Yes, I can't remember.
Because I saw one go up over here on 6th Street not too long ago.
Yeah, the really tall, they did 2-story on 6th.
Yep.
Right?
Yeah, and it's like this. So you get the styrofoam on both sides.
That's exactly what they are.
And so Home Depot's selling them now. And then just a little plastic connector, but then you throw your metal rebar down the middle, pour it full, and you're good to go.
There's a little bit of a connecting like wire system that goes laterally.
Little corrugation, yeah.
Yeah, and then you drive the rebar down vertically and fill it with concrete.
Get some good engineering right there.
And that's it. And then the styrofoam just stays there. It's you can drywall over it, you can drill into it.
Yeah.
They sell these things already pre-made with conduit run through them or with window sills or whatever. You can just, it's Legos, man.
Yeah. That's awesome. And then so what I would love to be able to do is put all the nasty styrofoam that comes out of the to-go containers and the deli, all that, and just packaging and peanuts. Just make this stuff locally with it.
Yeah.
We got to do it. I mean, that's turning the corner right there. Okay, guys, I think we're caught up now. Let's just see what's going on in week 7. Have you guys looked into it much yet?
Not a whole lot. A little bit.
Okay.
Just a bit.
All right. Let me see what I can.
I heard most of the chapter.
Let me see what I can. Okay, 109.
More than one.
137. I know I brought my book over here. Didn't you guys grab it? So chapter 5. So this is transportation from biorenewable energy resources. So they've got efficiency in here. You've seen that before in 101. The Brayton cycle. So this is mainly about energy. They even have an entropy equation here. Yeah, let me give you this. I want to highlight a few things in here. Grab my notebook. My textbook. Yeah.
The only plus side is that he reminded me of this is the midweek. This is like halfway through. I might make it till the end.
This grade's sucking in this class right now.
Is it? I'm suffering.
Like 75 or something.
I'm suffering in my trig class, same thing. I'm going fucking mid-C in trig, and it's just pissing me off. You know, like, I don't mind bees. Like, yeah, bees are fun, but I don't like it.
Especially if we don't have the opportunity to retake the class, maybe. We have to, not that I want to think of that.
No, but seriously, it's something to think about. Honestly, the only saving grace for me this semester is that everything I study in power systems this week, I just get to do in AC next week. You know what I mean? Like,
What do we kind of been dishing around each other? So
enough to keep me like afloat if they really take a big divergence. I'm kind of going to be a little apprehensive.
This is a really good textbook, by the way, in case you didn't notice. Yeah. Okay, so you're gonna meet Patrick Brown here pretty soon. But what we're looking at is the simplest way to derive bioenergy from biorenewable resources is to burn it. Now, one thing that Blue Marble discovered when they were trying to do the same thing, they were out in the ocean harvesting harmful algal blooms that were killing fish, and they were going to turn it into oil to burn. And they realized, okay, so I've got a barrel of this stuff, and it's worth maybe $100. But when they were presenting it, they realized, somebody approached them and said, hey, what you've refined here is actually food grade, and it tastes like blueberries, and you probably got about a $5,000 barrel. So kind of back to the Thujon thing, like what's the best use of this? The petroleum industry, makes some money from their combustion products, but most of it's from other things. So the petroleums are still,
So is it just because there was some kind of a compound in that algae that they hadn't banked on?
Yeah, just they were fine, and it was science, and the way they refined it ended up food grade, and I think that's how they got their start.
Awesome.
Yeah, kind of Willy Wonka style. Yeah. Okay, so direct fire furnaces either burn fuel directly in the process stream, or the flue gas from combustion is brought into contact with the process steam. So if we're looking at 5.1, fuel's coming in, air's coming in. The tempering air is basically there to make sure that you're getting to full combustion. We're going to do something similar with our rocket stove here this summer, so there's a couple different airstreams coming in. In the case, in B, you've got indirect water tube boilers. This is more like what you see in your house with your boiler, so the water comes through. Maybe it hits steam temperatures, maybe not, but there's enough pressure there that it runs the cycle. Okay. Now, and this is pretty key here. Let me read this. It says, although flue gas from the combustion of biomass, you were asking about this earlier, Damien, is primarily a mixture of nitrogen, carbon dioxide, and water vapor, and lesser amounts of oxygen. It also contains traces of alkali metals. So sodium is in fact a metal, potassium is a metal, it's also hydrogen chloride, and there's a little bit of chlorine. I mean, there's chlorine in our bodies, there's chlorine in plants, it's sort of it's an ion. There's sulfur, obviously, we talked about cysteine previously, and then NOx, nitrogen oxides. And of course, tar, which is said as a mixture of oxygenated organic compounds, so longer chain hydrocarbons.
It's like there's the creosote and stuff like that.
Yeah, creosote's another one, exactly, yeah. Creosote's just kind of like nasty, hard tar. It says, on the other hand, if the biomass is first converted to flammable gases, and this is what we're going to see at Brian Jackson's outfit. In fact, I'm tempted. We're going to sit down with Brian Jackson on Monday. Have you guys been in contact with him much at all about the? Okay. He's kind of a one-man show. I'm gonna talk to him about some business ventures, but we really also need to get you guys in the loop on the Biomax, because that thing needs to get up and running. So maybe what I'll see is if Brian Kearns is available to come down, because he's the Biomax expert and it's kind of his baby, and it might be good to have you guys go down with him. If not Monday, then some other time in the not too distant future. Okay.
Let me know if you make time to do that whenever.
Yeah.
So I'd like
Yeah.
to see that, you know.
I will. Okay. Now, one thing that I want to make really clear on efficiency in terms of the math. So let's just spend a little bit of time on the mathematics here. There's a couple different ways to write efficiency. You might see a problem like this on your homework. So eta max equals 1 minus T low over T high. That's kind of the more complicated way to write it, in my opinion. If we write it instead like this, equals T high over T high minus T low over T high equals T high minus T low over T high, or equals delta T over T high. What's that mean? Well, it means this. It means if you've got your fuel and you've got your oxygen going in, everything out here is T low and everything out here is T high. Just highlight that. So here's your low temp, your atmospheric temperature, and then inside is your hot. So that's efficiency, and that's Carnot efficiency, and it just basically means the hotter you can get the thing, the more efficient you're going to get it. So if you ever have trouble remembering this, efficiency always has to be between 0 and 1. So eta is going to be greater than 0, less than 1. And it's also, I think this is in this course as well, eta is also equal to 1 over the heat value. Have you seen that before? Okay, yeah. So that's something to keep in mind. I don't see I don't see a picture of it, but the book does mention the Otto cycle and the diesel cycle. So let's just go and let's look at those. The Ada that I just mentioned was the Carnot cycle. Let's look at these two. So Otto, these were early German engineers. Okay, and again, here's your T hot, here's your T cold. This is heat flow, and this is work coming out. Now, so here we are, Otto cycle. And again, it's idealized. Nothing works exactly this way perfectly. But let's just look at this in detail. So process from 1 to 2. So if we're going to go from 1 to 2, so it's adiabatic, so isentropic. It just means that the no temperature is leaving. Let's look at both diagrams at the same time. So if we go from 1 to 2, what's happening is the volume is going down. So just think of in your piston. So going from 1 to 2, the stuff's getting squished. It's also getting hotter. So work is being done on the fuel-air mixture in going from 1 to 2. Going from 2 to 3, that's basically your ignition. So everything gets hotter, but the volume doesn't change. The volume doesn't change, but the pressure goes up. So what's going on there is you're sort of at the top of your stroke. The thing goes off, but it's sort of stalled or delayed there, and the idea is it's not really moving, right? It's right at the top of that thing. It gets hot, the pressure goes up, the volume doesn't change. That's going from 2 to 3.
Gotcha.
So just think, regular old, car engine. 3 to 4. So now you've got all that pressure and temperature built up. As the piston goes down or it opens, obviously the pressure goes down, it gets colder, and work is now being done on the vehicle. You're sort of essentially pushing the transmission with that. Yeah, and 3 to 4, absolutely, yeah. The volume's getting bigger, going from left to right, going from 3 to 4. And then 4 to 1, constant volume. So in this case, you're sort of at the bottom. Volume is maximized right over here, going from 4 to 1. 4 to 1 here, the temperature is also diminishing. Now this other thing down here is entropy. I like kind of talking about that in detail. If you look at this, the entropy inside the engine sort of goes up and then comes down by the same amount. What we're not seeing is the entropy outside the engine. So on the outside, the air is getting a little bit hotter. So in general, if you see, okay, this guy's getting hotter, 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 entropy is increasing. When it gets colder, 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 the entropy decreases because everything's not all jammed together and mixed up as much. So anyway, that's the Otto cycle. The other one that's mentioned is the diesel cycle. Let's look at that in some detail. These diagrams, so it's the same thing. We're still going from something hot to something cold. Something is on fire.
This is like pressure instead of a spark.
Yeah, you use pressure compression instead of like having to start it.
The heat and pressure. increases until it combusts.
Mm-hmm. So in this case, I don't see, let's see if we've got a temperature.
Just usually do something in cool plugs.
Unfortunately, there's no temperature entropy diagram, but what's going on? So basically, this is the compression, and you would see a similar increase in temperature, like we just did previously with the Otto cycle. Here, it's getting hot, so you're again right at the top of the power stroke. The explosion happens, work is done on the engine. Now you're at the bottom, and then the heat is released from the engine through the valves. So, kind of similar thing, but just a different.
I've seen it on the diagrams like that too.
Yeah, yeah. I'm gonna go back. Let's just look at them together. Auto cycle. So in the case of the Otto, the pressure rises at the top. In the case of the diesel, it's assumed to remain constant. So I think more or less what's happening as this thing is coming up, at some point ignition is actually occurring, and I think that's maybe why they're not drawing the temperature, because it could vary quite dramatically depending on exactly when ignition occurs. But there's so much momentum already shoving that thing up. Here's at the top of the power stroke, and then it comes up. Okay, so that's power. The Stirling engine, I've got one over in the office. Actually, Tim has it. It says the Stirling engines and the Rankine cycle are relatively modest, but low maintenance, and you're not really necessarily setting anything on fire with the Stirling engine. It's also worth noting that the Rankine cycle, let me show you that guy really quick too. We've got temperature and entropy. Let's look at Rankine cycle. Yeah. Okay. So here's Rankine for pressure and volume. So in this case, you can still see compression occurs, so the volume goes down, but at a constant pressure. That's kind of the difference. In the Rankine cycle, the working fluid, and let's just look at a Stirling engine. There's no real exhaust.
It's because it's a closed loop inside of it.
Yeah, there's no real exhaust. There's some really good. There are some really good videos out there. Like I said, we've got one over in the office.
That's top ones.
Mm-hmm.
Those are awesome.
Yeah. Yeah. Okay. Yeah. So here we go. Let's just take a look at this. In the case of the Stirling engine, these two gases are attached. Let's do Stirling engine animation. Two-cylinder Stirling. There we go. So, there's no exhaust, but the issue and why the Stirling engines are not as efficient is they're not hitting as high of a temperature either. That's kind of the deal. But this is something where one side's out in the sun, the other one's attached to a geothermal source, or vice versa. There's your heat, there's your cold. The thing just kind of runs all day long. Yeah. We tried to build one a few years ago, but it's a challenge.
And to pressurize that system is going to be difficult too.
Well, you don't necessarily have to pressurize it. This is a 2-cylinder. There's also a 1-cylinder. See. Single cylinder. This is almost, yeah. So there's just the 1 cylinder. There's 2 separate chambers. That's just genius.
Yeah. It's
just genius.
And with as long as it's been in operation too, you know?
Yeah. My dream, I mean, honestly, I would love to see a mechanical power grid. You know, like right now, we pump electricity to our houses, we pump water to our houses, we pump gas to our houses. How cool would it be if there were just a bunch of universal joints underground with all these shafts? I mean, we were there 150 years ago with pulleys and horses and all that, but I just think it would be killer if, you know, the sun is shining up in my house, I got my Stirling engine going, and I just plug my fridge into it. Because at the end of the day, all your fridge is doing is just compressing a gas over and over again. It doesn't need electricity. It just needs to move the gases around. So you've got your mechanical grid, you plug your fridge into it, you plug your big ass fan, you plug your pump. I mean, all these things are just doing, or your table saw, what have you. And it's just running on a thermal gradient, not on a chemical combustion project. So anyway, that's my fantasy world. Steampunk, yeah.
That sounds great.
All right. Well, let's just end on that note. Again, this book is fantastic. The Brayton cycle, the combined cycle. Oh, one other thing I do want to mention. Sorry, guys, before I let you go, is that when you're looking at efficiencies, you have to multiply efficiencies. You can't add efficiencies. Because at each point in the process, the output from one serves as the input from another. So just as efficiency is always, let me write this down for you. So if you've got something that's thermal maybe, another thing that's electrical, and then let's just say, and this is kind of where we are right now. And really this thermal is slash chemical because you've set something on fire, you know, thermochemical. And then you go to your power grid, which is electrical, and then you go to your mechanical, which is your table saw, your fridge, or whatever. You're going to have some kind of efficiency, so I'll call that thermal, efficiency electrical, efficiency mechanical. So if you want your overall efficiency, it's the product of those three.
Gotcha. That makes sense.
And we even saw that early on in 101 with going from the power plant out to the light bulb. You multiply them as you're sort of losing all the way along. Okay, yeah. And then if you have questions on fuel cells, I'd be happy to get into it. I wish we were still teaching that. We don't anymore. There are a bunch of other types of acids and fuels listed here, so the sky's the limit. So very broad diversity of biofuels. All right, so let me know what you need. I'll see you next week, and then we'll have Patrick Brown and Brian Kearns in the next couple of weeks after that.